this week is next week. I know what church it is.
Fire hose. 4.
No, he mentioned it. Yeah, that's good. I mean, the only reason I haven't been to I feel that might take
Okay, we ready to jump in? Get back into carbohydrates. We'll actually finish the chapter today. It was kind of cool. You guys want? Does anyone want to clarify anything before we? Because it's going to feel a little overwhelming today when we get into disaccharides and polysaccharides. So we talked about what? Need a review. I'm going to do the whole lay it over, coil, form the hemiacetal, because we have to understand this. And it actually gets a little more complicated than that. Let go do that. All right, so happy Monday?
No.
Yeah? You have a good weekend?
It was cold.
Cold? Anybody else at Toby Mac concert? Anybody? Did you? Oh, you were in that car. Okay, she was in the car. Dark. That's cool. That's good concert. Super funny, yeah. My daughter got a fist bump with Toby Mac. She was so excited. I'm never going to watch that again. Okay, so carbohydrates again are the carbon source that most aerobic processes in the body burn. That's why we're going through this. So don't get lost in the weeds, because we do need to keep the forest in mind, because we're going to get to the citric acid cycle where we take glucose and we break it down into carbon dioxide and water and energy. Okay, that's where we're headed. We're going to burn this thing. Just like when you burn wood or paper in a fireplace, you're converting sugar, cellulose, which is made out of glucose, into carbon dioxide, water, and energy. Right? It's an exothermic process. Our bodies do it in a controlled environment, which was the miracle of it. It's not that we can burn anything with oxygen, but that our bodies do that at 98 degrees roughly. Okay? That's the miracle of being able to harness those energy, those electrons, on a controlled temperature scheme. Okay? So, with that, the glucose that we are all now experts on starts with a line and 4 threads like a football, with our aldehyde up top as carbon 1, our CH2OH at the bottom as carbon 6, and we go right, left, right, right, good, right, left, right, 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 right. Okay, that is glucose. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So glucose is C6, H12O6. Okay? So it's a carbohydrate. Carbohydrate. Carbon with hydrogen. Or carbon with hydroxyl groups. Okay? So which one of these is our special oxygen? Which one of these is our special alcohols? Carbon at 5. Why is this one our special one? Well, I memorized it, but why is that the special one?
It's the furthest chiral carbon.
Furthest chiral carbon from the carbonyl. Okay? This one's chiral, this one's chiral, this one's chiral, this one's chiral, this one is not chiral. So we back up. Oh, that's the special. Okay? It is this alcohol that is going to react with this aldehyde to form the hemiacetal. Okay? That's where we left off on Friday. So when we did this, we laid this thing over on its right. No mystery to that. I'm going to go up here just because I'm going to kind of come around really frustrated with this thing. So I'm gonna lay it down on its side. No, seriously, the reason why we're in here is because I only use whiteboard. Otherwise, we'd be over in the business building. But Dr. Nixon, I teach the class at the exact same time, and she wanted this room as well, but she uses overhead. I don't until I get to biochemistry. So it's just frustrating because I love chalkboard space. I love whiteboard. It's just frustrating. Frustrating. Okay, just frustrating. Okay, so there's my carbon 1 as I lay it down on its side. There's my farthest one away, HO, H2C. Okay, and when I look at it, I'm going to go right, left, right, right. Right, left, right, right. Okay. My special bond is between 2 and 3, so I'm just going to make that a little bit. And then I'm going to coil it. So when I coil it, it looks like this. Okay. Again, here's my special. And if it helps you to see this by numbering it, do so. Carbon 1, 2, 3, 4, 5, and 6. Carbon 1, 2, 3, 4, 5, and no, 6 is right here. Okay? Good? All right. So with that, we're going to make our lines. Okay? And what do I have? Well, this is going to be a CH2OH. This is going to be, when I look down, it's going to be right, left, right, left, right, right. There you go. Okay, that's all we did. So all I've done is take my right, left, right, right, laid it over its side, coil the tails up. And again, like I said on Friday at the end of class, we got a little bit hurried at the very end. But this molecule literally is really wanting to coil. So if I make this molecule, if I make glucose with a molymod, you can see that this thing is like wanting to coil. So if I actually make this, so there's our Fisher projection of this thing. Okay. Right, left, right, right. CH2OH down here, and an aldehyde up here. So what's going to happen is this alcohol right here is the one that's going to come in and bond with that. Okay? So what we're actually going to get is this here. Okay? Okay, cool. So let's put this. Now, here's what it's fun. It's a okay. So here's what we're going to make. Now, this carbon right here, this carbon right here is the special carbon. It's still the special carbon. It's carbon 1. Right? This carbon right here has a carbon, a hydrogen, a hydroxyl, and an O carbon. Okay? So that is a chiral carbon. Right? That's the special. We call that an anomeric carbon, and I'll describe what that means. Okay, so this isn't quite ready. I need to have this oxygen into this plane. So what I'm going to do is I'm going to rotate around that bond. And single bonds, remember, rotate. Double bonds do not. So I take and I move this to here. I move this up to here, and I move that down to there. Okay? So I'm just going to rotate. I'm just going to rotate that around to put this oxygen in the plane of the ring. Okay? So when I do that, notice I draw everything the same, but the OH is now in the plane. Okay? Okay, now we're good to go. Okay, so here's where I said it's going to get a little bit more complicated that I didn't describe on Friday. So when this thing forms the hemiacetal, okay, this is kind of a big deal. It's the difference between cellulose and glycogen and amylose, which we'll see. So when I make this the actual, go back to the actual aldehyde. open this thing back up. So yeah, I'll put you back on there. Let's put you back on. Okay, so here's what's happening with this aldehyde. And this is an important thing we need to discuss and describe. When the hydroxyl group, when the special hydroxyl group approaches this aldehyde, since the aldehyde is planar, since the alcohol approaches the aldehyde, and the aldehyde is planar, well, let me set up. Okay, so when this alcohol right here, our special, watch this. When it approaches the aldehyde, see the aldehyde up here? Remember, the aldehyde is trigonal planar, okay? So when this alcohol, our special alcohol, comes in, notice it can either come in from the bottom or it can come in from the top. Okay? So that means that when I form my actual hemiacetal, I'm going to do blue and red. So blue, if blue comes in from the top up to and hits the carbon, it pushes the hydroxyl group down. Okay? So blue is here. Blue looks like this. Okay? So the hydroxyl group comes in and pushes it down. So this is the new, this is my special, this is chiral. This, because it's on the bottom of the ring, we call this an alpha hydroxyl group. So this becomes alpha D glucose. Okay? Alpha meaning the hydroxyl group is down. Because watch what's going to happen when I do this a different way. If I take the hydroxyl group and hit the bottom of the, okay, that's going to push the hydroxyl group up. So that looks like this. Okay? Notice my hydroxyl group is up. This is called beta. Okay? So that makes this beta D glucose. Now you might think, well, why does that matter? It really does matter. It matters because depending on the polysaccharide and the disaccharide depends on the nature of, and the location of this hydroxyl group. Okay? There's a reason why we cannot digest a cotton shirt if we eat it. We can eat a cotton shirt. It would just be like eating a carrot with not as much nutrients, but it would basically just be like roughage. That's what cellulose is for us. But a grazing animal like a goat, cow, horse, anything that chews a cud, they actually have a bacteria in their body that breaks down cellulose. It has an enzyme that breaks down the beta-1,4-glycosidic bond. We do not. Neither does the animal, by the way. It is the bacteria in the animal's body that actually does it through its multiple stomachs. Because we can digest the alpha D-glucose, which we'll see in a second. Right? That's in amylose, amylopectin, glycogen, the way we store our energy. Okay, that's the alpha is special for us. The beta is what, again, what plants have, right? That's the way they store their glucose. Both are D-glucose. D-glucose is the sugar molecule that pretty much all of life uses. There are a few other sugars, but that's the main dominant sugar that we use, okay? Are we tracking alpha and beta? This is called an anomeric carbon because this process keeps opening up and closing, opening up and closing, opening up and closing, okay? This is slightly more stable than this one. Oops, excuse me, this one is slightly more stable than this one. Not gonna get into why that is because it really doesn't look like this, it looks like a chair, but that's just a little bit more chemistry than you're gonna want at this point. But this is slightly more stable. The way you can think about that is this hydroxyl group is up, this hydroxyl group is down, so they're the farthest away from one another. This one's up or farthest away from that one. This one's down, farthest away from that one, because that's a bigger group. This is farthest away from that. So it does form a slightly more stable than having these two hydroxyl groups. Not much, but enough that the beta is slightly favored, okay? So all we did here was, again, drew glucose, tipped it over, coiled it, rotated, formed our hemiacetal. We good? Ish. So what happens when a hemiacetal reacts with another alcohol? What's it form? Okay, we'll go back up. What's hemi stand for? No. No. Hemi stands for something special. They're actually both circled here. Hemi stands for the hydroxyl group of the hemiacetal. Okay, remember, an acetal and a hemiacetal differ by the presence of the hydroxyl group. The hydroxyl group tells me that this carbon is a hemiacetal because it's hydroxyl, hydrogen, carbon, O carbon. That's by definition from Friday what a hemiacetal is. Carbon with a hydrogen hydroxyl, carbon, O carbon, okay? So with that, if I react a hemiacetal with another alcohol, I get a acetal. I get an O carbon here. That's where we're headed. Okay, that's what a disaccharide is. These are the monosaccharides, and then we'll also see polysaccharides, okay? Before we go there, what is the difference between glucose and galactose?
The first hydroxyl group is
No, which hydroxyl? You're right, but which hydroxyl? It's a C4 epimer. And what's an epimer? It's a C4 epimer. So what happens as a C4 epimer? It flips. Meaning this one flips. So this one, 1, 2, 3, 4. So in galactose, this is flipped. Okay? In galactose, this is flipped. Does that make sense? So this entire process, we could have just done the entire process with that flipped, and we would have made galactose. That's the only difference between glucose and galactose. The only difference is this is flipped and this is flipped. You have alpha D galactose if that's flipped. You have beta D galactose if that's flipped. Make sense? The one that's a little bit different is fructose. So fructose, we have to describe. Fructose is what type of a sugar? It's a ketone. So your book, and hopefully Dr. Nogales in lab, will describe it as a non-reducing sugar, meaning it will not reduce toluenes or phthalate or any of the tests that test for aldehydes. Okay? So fructose is non-aldehyde, so it can't be oxidized. The ketone carbon is fully oxidized. It can't be oxidized further unless you burn it and convert it to carbon dioxide. So this is what we call a non-reducing sugar. But let's describe the nature of this sugar because it is slightly different when we do the whole tip and curl thing. But just like I did before, we're going to do right, left, right, right. Okay? So carbon 1, 2, 3, 4, 5, and 6. It is still a C6H12O6 sugar. It's just a ketone instead of an aldehyde. So when I tip this, I tip it over. Again, do the exact same thing. CH2OH, carbonyl with my threads. Carbonyl here. Again, when I look at this, it is right, left, right, right. Okay? Special moves over one. It's this one right here. That's my special. If it helps, number it 1, 2, 3, 4, 5, and 6. Okay, good. So now I'm going to coil it. So I'm going to keep my, I'm going to go ahead and put my ketone out here. Here's my special carbon, my 2 carbons that are coiled, or that are coming out at me. Okay? So I've got 1, 2, 3, 4, 5, 6. Okay? So if I put all this in, CH2OH, again, when you do this, it's going to be right, left, right, right. And again, notice where my hydroxyl group is. Here's my special hydroxyl group, here. Okay, it's carbon 5. So again, this is my special. So it's carbon 1, 2, 3, 4, and 5. So this is my special. So with that, I need to put my special oxygen in the plane of the ketone. So what am I going to do? I'm going to rotate it. So I'm going to put this hydroxyl there, that up there, hydrogen down there. Okay? So when I do that, notice my rotation then looks like this. Okay? And we're good to go. Same thing. If I come in from the top of the ketone, it goes to this form of fructose. Okay. And then pushes it down. So the hydroxyl goes down, up, okay. So which one is that? Is that alpha or beta? So here's the plane of the sugar. It's this one that is my anomeric that opens and closes. In this case, it's a hemiketal, not a hemiacetal, because it did come from a ketone, not an aldehyde. So is this hydroxyl group below the sugar or above the sugar? Below. Is that alpha or is that beta? Alpha, good. So this becomes alpha D fructose. Okay? So you have 2 different forms of sugars. Some sugars are 5, some sugars are 6. Okay? This is a 5-member ringed sugar. Okay? This is what we call a furanose. This is what we call pyranose types of sugars, okay? Furanose you're gonna see throughout. So the two pyranose forms are gonna be galactose and glucose. Really, we're gonna see other furanose forms. Right here, we're seeing it fructose. Also fucose, which is actually one of the identifiers in blood, is actually also a furanose. But we're gonna see this when we get into DNA. Deoxyribose. Ribose is also a furanose, okay? So we're gonna come back to the furanose system when we get to DNA in a few chapters, when we see the backbone of the nucleosides and nucleotides, okay? All right, so if I close this from the bottom, it goes to, of course, this form. Again, still a furanose. Okay? And in this case, it puts the hydroxyl group up. And so, again, we'll put this here. Okay. Cool. And that's it for monosaccharides. Kind of the big deal with monosaccharides, they, glucose, galactose, and fructose, they actually form rings. They actually prefer either, what we're gonna see, this is the intermediate. It doesn't prefer the hemiacetal. It either prefers to be open as the aldehyde or to be closed, completely closed as the full-blown acetal, which is where we're headed, okay? So this is the way these sugars are processed within our body. Sucrose has glucose and fructose in it. All right, so table sugar is a disaccharide of glucose and fructose, okay? Good? Good? Okay, let's build on it. Well, that's complicated. Okay, so we move into these things called disaccharides. So what do you think a disaccharide is going to be? Yeah, probably have two of these things, all right? So if we take glucose, if we take glucose and form a ring from it, okay? Okay, so which sugar is that? It's glucose. Be more specific. Give me its full name. Alpha D glucose. How do I know that that's alpha D glucose? Okay, yeah, good, right. Alpha has those together. Okay, or alpha has the hydroxyl down. And I wish they had reversed that, just for the record, because it makes more sense to me that beta would be bottom. That made more sense, but it's not. Beta is top, alpha is down. So those carbohydrate chemists just mess everything up. Okay, so with that, let's take and put another alpha D glucose right here. So if I put another alpha D glucose right here, okay. Yes?
I have a question.
Yes.
So, like on the carbons, like you have H, HO, or like OH?
Yeah.
Like, what's the difference there?
Yeah, none.
No,
I agree. And that kind of little stuff I know drives you, I know, I'm sorry for that. It doesn't matter.
Okay.
Yeah, good. It's a good question. Whether I do this or this matters not.
Okay.
Yeah, I'm sorry for that. And the other thing you'll see me do every once in a while, I'll do this instead of this, okay? They're the same. And I know that drives people crazy, but in my brain, I actually hate this. but all books do it. It is actually that. But I know your book has this, so I try to keep consistent with that. But I don't teach it that way in organic, I teach it that way. So I have to remember which class I'm actually teaching. But thank you for clarifying that, because that is frustrating and I realize that. Okay, that is a horrible age, but that is an age. Okay. All right, we're gonna make a disaccharide, but here's how we're gonna do it. We're gonna do it through a dehydration process. Go back to dehydration. What is dehydration? Removing water, good. So this process here removes water. Well, what happens when I take an aldehyde and react it with an alcohol? I get a hemiacetal. Okay, that's what we talked about. Right? Go back in your notes from Friday. That's what I hope that's, or Wednesday, I don't know what we talked about that. Okay. If I take another alcohol, what do I get? An acetal, okay? I get a full-blown acetal. So I go from aldehyde to hemiacetal to full-blown acetal. So follow this. Here I've got a hemiacetal, right? That's a hemiacetal. Came from an aldehyde. We just made that, right? Carbon, OH, R, OR, H. Hemiacetal. But notice what happens when I bring another alpha D glucose next to it. I have an alcohol. And what happens when I take a hemiacetal and I react it with another alcohol? I form an acetal. So watch this. This alcohol at 4, remember, 1, 2, 3, 4, is an alcohol that can attack the carbon. And when it does, watch what's going to happen here. I'll circle it in green. I'm going to remove, what am I going to remove? Water. So the alcohol at 4, remember it's fused, doesn't flip. The only one that moves up and down is 1. And that's because it's opening and closing to an aldehyde. These are all fused. Okay? So at 1,4, you don't even have to call it alpha. I know it's down because it's glucose. If it's up, it's galactose. Okay? So you don't have to call that alpha 4. Only alpha here because, again, that's the one that opens and closes. So here, if I get rid of water, watch what happens. I form minus water. Okay? So just like if I have a hemiacetal and I react it with another alcohol, I get an acetal. Notice this carbon just went from a hemiacetal to an acetal. So it's H, OR, carbon, O carbon. H, O carbon, carbon, O carbon. H, carbon, O carbon, O carbon. So this is an acetal. This is still a hemiacetal. I haven't added anything over here. Okay, because the OH tells me it's a hemiacetal. So this carbon is now locked. Acetals are stable. They're actually very stable. Okay? They're stable under base conditions. They open up under acid conditions, which might be the reason why our pH is 7.4 in the blood. If it were lower, oh, these would unravel. Okay, so with that, this is now called a alpha 1,4 glycosidic. Is that with a C? Glycosidic? Is it a C or an S? C. Is it a C? I hate spelling. Glycosidic bond. Is that right? Glycosidic? Is that right? Oh well. C or an S? I don't really care. Is it an S? It's a C? Is that right? Well, anyway, that's the bond. Okay? Glycoside, glycosidic. Okay? So this is an alpha 4. Somebody look in their book and see how to spell glycosidic. This is bugging me. Is it an S? You're pretty sure it's an S? I'm going S. That just looks so weird to me. Okay, I'm going with that. If that's wrong, fix it. But it's a alpha 1,4 glycosidic bond. Now break this down. Alpha 1,4. Why do you think I need to call that an alpha?
Because the hydroxyl groups are in the bottom.
Yep, because this hydroxyl group is alpha. Remember, it was down. So it's an alpha 1,4. I don't have to say that it's a 4. I know it was down because, again, it's glucose. This makes, by the way, this makes maltose. You might have heard of maltose. It's in malt. Okay? Okay? Yes?
So is it 1 because it's on the first carbon of the...
Yes. The alpha describes the nature of 1.
Okay.
I know 4 is alpha. I don't need to say that.
Okay.
4 is down because it's glucose.
Okay.
Yeah. It doesn't move. It stays down. Okay? This is maltose. Kind of cool? Now watch what happens. Let's build on it. Shall we? It's complicated. Okay, so maltose then, guess what maltose can do? Maltose can bring in another alpha D-glucose. Okay, notice I just brought in another alpha D-glucose. Okay? Tracking how this is working? What do you think I'm going to do? What am I going to do to it? What kind of reaction am I going to do? I'm going to dehydrate it. So let's dehydrate it. Let's remove water. Oh, water's gone. Okay? It's gone. Water's gone. So if and I just like to redraw it, I could bring it over here and kind of look dorky, but I'm going to do it this way. Okay? Now, I no longer have maltose. Now I'm building a polymer. Now we're moving over into, and here's the way I'm going to do this. I'm just going to put oxygen with this here, meaning it just goes on. Okay? And likewise, over here, it just goes on. Okay? Builds. And this now, not maltose. Maltose is 2. Maltose is a disaccharide of 2 alpha D-glucoses. This now makes amylose. And who's heard of amylose? We eat it every day. Comes in the form of potatoes, pasta, rice, starch. Okay? Amylose is an alpha 1,4 polysaccharide. Okay? And it goes on, and it does this really kind of cool coiling thing. Amylose looks like this. It makes these coils. All right? But here's the thing. Amylose makes up about 20% of all starch. There's another form called amylopectin that makes up the other 80. Amylopectin is different than amylose. All right? How is amylopectin different than amylose? Well, here's how it's different. It actually takes this carbon right here. Check this out. so this one here okay, notice this one here is what kind of a linkage? What kind of a linkage is that? See if you can describe that. Someone throw it out there. Just be brave. I won't be mean. What? Describe the type of glycosidic bond this is right here. Who said it? Alpha? Okay. What carbon is this? It is carbon 1. What carbon is this? 1, 2, 3, 4, 5, 6. So what type of bond is this glycosidic bond? Is this below or above the sugar? Therefore, is it alpha or beta? So it's an alpha 1, 6. Alpha 1, 6 glycosidic bond. Yes?
It's not really just, is the amylose alpha 1,4 or is that 2?
Amylose is only alpha 1,4s. I'm building on this. That is only alpha 1. Amylose is only alpha 1,4s. Okay?
I didn't know if that was a 2 or not.
Oh, alpha. I'm sorry. That's a weird alpha. Yeah, it's only alpha 1,4. Okay? But what do I have here? Alpha 1,6. So here's the thing. Amylose is only alpha 1,4. Okay? Amylopectin is alpha 1,4, but about every 25 glucoses, you get an alpha 1,6. So it's different. It's not just a single coil like amylose. What it actually does is kind of cool. It actually coils, and about every 25 it has an off coil. And about every 25 it has another off coil. And about every 25 it has another off coil. And then every 25 it has an off coil. And so you see that it's a denser form of glucose. So amylose is about 20% of all starch. It only has alpha 1,4 coils. Amylopectin is primarily alpha 1,4s, but about every 25 monomers or glucose units, it has a branched off alpha 1,6. That kind of cool? So this then becomes amylopectin. Isn't that kind of cool? And so now the last one of that family is glycogen. Have you ever heard of glycogen? What's glycogen? What's glycogen? Anybody want to take a stab at what glycogen is?
Isn't it like a stored form of glucose?
Yeah, who stores it that way? Mammals, yeah, we do. Okay, so amylose, amylopectin, and glycogen. Glycogen, notice this is important, are also alpha 1,4, but about every 10 to 15 you get an alpha 1,6. Meaning, glycogen's even a more dense storage of glucose within the body. So those are your 3 polymers, or your 3 polysaccharides so far. We have 1 to go. So let's review. What is amylose made out of? Glucose, and what type of glycosidic bonds? Alpha 1,4. Okay? Amylose is a polysaccharide with alpha 1,4 glycosidic bonds right here. Amylopectin is different from amylose. How?
25 glucoses of alpha 1,6.
Exactly. About every 25 glucose units, it has an alpha-1,6 branch. The alpha-1,6 comes from bonding to carbon 6 and forming an acetal at carbon 1 in the alpha position. Okay? Glycogen is about every 10 to 15, meaning it's more dense, but it has the similar structure to amylopectin. It's just more densely packed. Okay? Meaning you just get more coils in here. Okay? So you just have more coils in there. It's just denser. Okay? Are we good? Yay. All right. Let's do our last 3, and you guys mastered carbohydrate chemistry. Yay. Okay, the last one, the next, I should say, disaccharide is lactose. Now, this is a nice little segue into why it is that our society is so overly obsessed with milk. We're the only creature that still drinks milk past infancy. Maybe we shouldn't be doing that. In fact, most of the time people have massive allergies. The first thing a physician's going to do is say, well, go off milk, because we have a lot of problems with milk. But I'm just saying. So lactose is a little bit different molecule, okay? Lactose is actually galactose, okay? Remember, how is galactose different?
That's the epimer at 4.
That's C4, good, C4 epimer. So this one is up, not down. Okay, good. And it brings in an alpha okay? So notice this is beta D galactose. This is alpha D glucose. Okay? So if I form a glycosidic bond between my hemiacetal and carbon 4 on glucose, I'm going to do a dehydration. So let's dehydrate. Gone. And we just formed lactose. Okay, so that is lactose. Lactose has a beta 1,4 glycosidic bond. Notice it's beta because it's up. Probably the reason why a lot of people have allergies to milk and dairy is because of the fact that it is beta 1,4. We don't have the enzyme that can process that, so we deal with a lot of times people that are lactose intolerant is because they don't have the ability to process this. Okay? So that's an important thing. This is lactose. Lactose is very similar, by the way, to cellulose. Okay? So cellulose or cellubiose looks like this. Are we all tracking with that as lactose? Yeah.
What did you use? Dehydrate and the beta?
Yeah, dehydrated at 1 and 4. Yeah. So if you remove this, remember dehydrate, removal of water, then puts my glycosidic bond between 4 and 1. Okay? So it's between 1 and it's a beta 1. Okay? Good? Ish? Sort of? Whatever. Okay? All right. I think I'm kind of fire hosing you guys today, so let's do 2 more and then we'll save the last 2 for Wednesday, and then we'll get into back to organic chemistry. How fun is that? Okay, this is lactose. stay with me. I know it's easier for me if you're taking notes, but if I go back to glucose here, get rid of galactose, I go back to glucose, I'm going to go back, I'm going to take my glycosidic bond here. Okay. I'm going to go back to beta here. Notice, this is beta D glucose. This is beta D glucose. If I make a polymer of beta D glucose and just keep on going, right? Notice it's a beta 1,4 just like lactose. But now if I make a polysaccharide out of beta D glucose, this is cellulose. Cellulose is a polysaccharide with beta 1,4 glycosidic bonds. Okay? And this is the one that our body cannot digest. We don't have the enzyme within us that can break this down, which is probably why even with lactose, it's a similar problem. So we take lactase as some type of supplement before you have ice cream if you're lactose intolerant, and that enzyme actually can break it down. Similarly, cellulose cannot be broken down. So when we eat cellulose, something like when you eat a carrot, that really is so important. That fiber that we cannot digest is so important for health. It's literally like a Brillo pad that just goes through our entire system, cleaning it. Okay, very, very important that we have that roughage within our diet to keep keeping our health of our digestive system. Okay, so we cannot digest this. How do we use cellulose? Cellulose is massively important, of course, right? We burn it, we make paper out of it, we make shirts out of it. Cows eat it out in the field, make this beautiful thing called steak. So we have this all through our society. But again, it's very important to understand the only difference between amylose, amylopectin, and glycogen is the fact that this is a beta 1,4 instead of an alpha 1,4. That's it. They're all D-glucose. It's all the same sugar. It's just how does it come together? Isn't that crazy? One bond flipped, and it becomes a completely different use. It's crazy cool, right? Okay, I think I have some overwhelmed faces out there. I'll finish this on Wednesday. I'll finish it on Wednesday.